Thank you. So, a very good evening to all of you. So, today's webinar session is about Introduction to Advanced CFD Analysis. So, the agenda of today's presentation is like we will go like this: a brief introduction to Computational Fluid Dynamics, then responsibilities of a CFD engineer in an industry, then governing principles of Computational Fluid Dynamics, CFD workflow, applications, softwares, and challenges, and job opportunities. So I will try to keep as much as simple. We will not go into any mathematical complications of computational fluid dynamics. So mostly the presentation will be like industry oriented, application oriented. So coming to the definition of computational fluid dynamics. So it is the science of predicting fluid flow phenomenon by solving mathematical equations using numerical methods. For what? For characterization of flow fields using high performance computing. So as you all may be knowing that the governing equations of fluid flow, that is the Navier-Stokes equations, they are actually second order nonlinear partial differential equation. And for complex problems, there are no exact solutions available for these equations. But you might have studied in your curriculum that for a simplified problems like flow through a circular pipe or flow between two fixed parallel plates using the initial and boundary condition, you can simplify the Navier-Stokes equation and you can obtain solutions for velocity profile or flow rate or pressure drop, etc. So that is like wherein there are certain problems we can simplify it and we can find the exact solutions. But in most of the cases, in reality, many of the engineering applications, including fluid flow, are complex and which cannot be simplified and solved like that. So in those scenarios, we go to numerically solving these governing equations using a computer. So basically what we do, this you might be knowing, but still I will just give a brief introduction. So we will discretize the fluid domain or the problem domain and we approximate this partial differential equation to algebraic equations and we solve for each of the cell in the discretized domain. So there are different discretization methods you might be aware, like finite volume methodology or finite difference methodology or finite element methodology or lattice Boltzmann method, etc., etc. So all these methodologies, what is common is that if the partial differential equation, that is the Navier-Stokes equation, that is approximated as an algebraic equation, and it solves numerically. It is an iterative process using a high performance computing. Okay, so why do we do this basically? Because we need to, what is our objective of doing this? So we need to predict velocities, pressures, shear stress, forces, temperatures, etc. And why we require this? Because we want to ultimately optimize the design of the product, or we need a better design of any better design, or we need a better performance, or we need a better fuel economy, or we need a less drag, or we need to predict the heat transfer in a boiler, or heat transfer of a hot fluid flowing through a pipe, or we need to optimize the piping network. So these are various applications that we will see in the coming slides. So that is the overall objective and introduction to computational fluid dynamics. Okay, so now coming to the responsibilities of a CFD engineer in an industry. So that is like, say, in any company, like there will be a CFD team and the CFD engineer will be a part of this team, and based on his experience he may be taking care of multiple projects or a single project or part of some project, but anywhere for an entry level professional, these are some of the basic roles and responsibilities. That is first and foremost is study of the input CAD geometry and pre-processing it. So when I say the study of input CAD geometry, he should be aware of what problem he is going to solve. Then he should know the real application of that particular problem. Then he has to modify the CAD geometry or clean up the CAD geometry to meet the requirements of CFD solutions. And that includes CAD cleanup. Then he needs to do the meshing, then solver setup, etc., etc. Then he should have a thorough understanding of the fluid flow physics. That is actually essential for setting up of the problem with proper numerical methods, flow, the type of flow, the boundary conditions, the turbulence models, the convergence criteria, etc., etc. Then obviously after solving, computer will do the solving part of it, so the individual don't have to actually worry about it. Then after the solution, actually the important part comes the interpretation and meaningful conclusion of the CFD results. Then obviously report generation. And once the results are analyzed, he may need to suggest the design modifications based on his results. Then in certain kind of problems, he may be dealing with achieving certain design targets, like optimizing the pressure drop in a pipe, or optimizing the flow distribution, or optimizing the drag coefficient, lift coefficient, such things. So in those scenarios, he might have to do a lot of design optimization studies to achieve those targets. Then obviously the teams work in as a collaborative environment, so different teams will be interacting with the CFD teams. So they have to hold on discussions with cross-functional teams to convey the results and design modifications, etc. And to a senior level or senior member in the team, they will be attending project meetings to understand the cost, quality, and target specifications of the product. So these are the core responsibilities of anyone who would be a part of CFD team in any industry. So now coming to the governing principles of CFD. So basically it all starts with governing equations. So you all know what is a governing equations of fluid flow, Navier-Stokes equation, and how it comes, what it represents is any governing equations of any phenomenon is the mathematical representation of that particular phenomenon. So the physical phenomenon we convert into a mathematical equations, so that we can obtain solutions for that phenomenon or characterization of that phenomenon. So we have, like in Navier-Stokes equation, we have momentum equations, x, y, z momentum equation, and there is a continuity equation. So we have mass conservation and momentum conservation, and wherever the heat transfer is involved, we couple these momentum equations to energy equations. Otherwise, if heat transfer is not involved, it is just we are solving the momentum equation plus mass conservation equation, that is well-known continuity equation. So we have the governing equations now in mathematical representation. Now what we have to do is, we have our problem domain, and we have to we are approximating this partial differential equation to algebraic equation. So that is the mathematical side of it, but that anyhow software will do. But what we have is, we have the CAD geometry in front of us, and we all have to do finite volume discretization. Meaning finite volume discretization is nothing but whatever the domain you have, that you have to divide it into cells and mesh in simple terms. And for each cells in the domain, these algebraic equations are solved, and you will be finding the flow parameter of interest, whether it is velocity, pressure, density, or whatever it may be. So that is the spatial discretization. And another part is temporal discretization, because the flow may be steady or unsteady, depending upon the problem and assumptions. Sometimes we approximate the unsteady problems are steady state. Actually, all the flow problems are unsteady, but we, with certain reasonable approximations, we could able to find average quantities by approximating it as a steady state problem. So in those scenarios, we have the temporal discretization, that is discretization in time. So there are different schemes available in the CFD solver. It's called explicit schemes and implicit schemes. Explicit schemes are those in which, if you are so I said before, this is an iterative process. So if at a time step, at a particular time step, if you want to calculate the flow parameters, then in an explicit scheme, you would be knowing the previous time step values, and that would be used to calculate the current time step values. So that is called explicit time marching. Whereas in implicit schemes, you would not be knowing the previous time step values and current time step values, and you will end up with a set of equations in the form of Ax is equal to B. It's a system of linear equations, and you solve all these equations simultaneously using certain numerical schemes. So those are called implicit schemes. Okay. Anyhow, like since in industry people use commercial codes, so they don't have to actually worry about this. These are the things which happens in the background of the solver. They have to select the right schemes based on the flow problems. Okay, and so spatial discretization over, temporal discretization is over. Now coming to the flow type, as we all know, like most of the engineering problems or flow problems are turbulent flows. Only very few cases where the flow is quite orderly flow, wherein we call it as a laminar flow. But most likely it will be turbulent flow. Then there are certain turbulence models are there to model this kind of turbulence flow, which we will see in detail in the coming slides. And another last but not least is the setting up of the boundary condition. Why it is important is, so as I said before, we are approximating a real problem into a numerical solution. So we need to know the actual boundaries of the problem so that we can specify. So what is at the for our computational fluid domain, we can specify the boundary, which will be the representation of the actual values in case of the actual problem. So there are different boundary conditions, like inlet boundary condition. So inlet boundary condition, it could be a velocity inlet or pressure inlet or mass flow inlet. So depending upon the problem, we have to arrive at the right boundary conditions. So these are the governing principles of any CFD application, whether it could be FDM, FPM, LBM, whatever it may be. So mostly these things are like which is already coded and inbuilt in the commercial solver. So we just have to pick the right options and run the solution. So that knowledge we require, but the coding part, that is not the scope of this webinar. So that is altogether a different field. Now coming to the CFD workflow. So this is what, like from a user perspective of a CFD software or an industrial application, like most of them will be working with. So the first part will be pre-processing, second part will be solver setting and solver calculations, and the last part will be post-processing. So pre-processing involves, so from the designer, one may receive the geometry, then he may need to know what needs to be required for his CFD problem. Those domains he has to extract, clean up other things. Then he has to extract the fluid volume. He has to define this inlet, outlet, or other boundaries. He has to generate surface mesh. He has to generate volume mesh. Then the quality has to be cleared for both surface mesh and volume mesh based on the type of the mesh. Then after that, the solver settings part will come. So in that, he has to select the right flow models, whether it is laminar, turbulent, and fluid, define the fluid properties, then numerical methods, boundary conditions, convergence criteria, the parameters which he needs to monitor for the convergence, etc. And obviously running the solution. Then comes the post-processing part. So that is the of parameters which is of interest. So it could be velocity vectors, velocity contours, streamlines, flow recirculations, flow separations, or it could be forces, drag, lift, or it may be the heat transfer coefficient, or it could be the temperature distribution. So depending upon the application, the person or CFD engineer can extract his parameters of interest, and accordingly he can move forward with design modifications or optimization, whatever, based on his objectives. Okay, so we have understood a general workflow. So we have got we got some geometry, we did some processing, and we ran the solution, and we got some results. Then how do we confirm that, okay, I have got a consistent, accurate results? How do we confirm that? So that is actually a very challenging and tricky part of this CFD simulation. So whatever we run, we get some colorful results, but sometimes it may not make meaningful conclusions. So in those scenarios, actually we have to, so there is a concept called mesh independence. So our solution whatever the solutions we obtain, it should be actually independent of the mesh. So here, as you can see, this is the geometry. Okay, so this is a straight pipe that convergence, and then there is a straight constructed portion, and there is a sudden expansion. So here you can see M1, M2, M3, M4. Now the only difference in M1, M2, M3, M4, as you see, is the total number of elements in this domain. So M1 has got, say, 6.3 lakhs elements, M2 8 lakhs, M3 1.2 million, and M4 3.1 million. Okay, so these are these four has got different elements in the increasing order of number of elements. Okay, and as you see in this problem here, there is a red line. So this is the center line of this problem, and along this center line, the velocity is plotted, as you can see in the graph. So there are four curves you can see, right? One is orange, blue, then one is yellow, blue, orange, and another shade of blue. So what is that one thing you can observe here is, see, all the velocities, I mean, for all the four meshes, you are not seeing a consistent velocity pattern. So you see the difference here, you see the difference here, you see the difference here. So for each mesh, we are getting a different velocity profile along the center line. Actually, this should not be happen. Actually, whatever the mesh, your result should not change with mesh. You have to get a consistent velocity for all kind of mesh. So I just want to show the difference. That is why I have put a different meshes, so that you would observe the differences in the velocity along the center line. But when you start doing it, you have to actually get this profile. Like if you are comparing 2 or 3 meshes, you should get a same velocity profile for all the meshes. So accordingly, you should choose that mesh for the studies. So that is one thing, like every CFD engineer should aware, and you should confirm before starting with any big project. So now that is one part. Now second part is like, how do we ensure that, okay, we have ran a CFD simulation and we have got a results, but how do we make sure, okay, I have got, or I have modeled almost close to the real world problem, and what is the, and my accuracy is almost 100%. How do we ensure that? So that is actually one of the challenging task of any CFD simulation. Not only CFD, any computational methodology, whether it is FEM or CFD. So one has to actually make sure that he or she is modeling the real world phenomenon as close as possible. So there are limitations. One cannot achieve 100% of real world problems, because that may require extensive computational power, and it is highly expensive. But then we have to make sure our errors are within the acceptable limits. So there comes the two terms, that is verification and validation. So verification is nothing but, if we go as per the definition, it refers to the accuracy of your numerical solution. So that is actually dependent on what your mesh, how good you have designed the mesh, your spatial and temporal discretization accuracy, your numerical methods, your higher order schemes, etc., etc. So where were we? Yeah, verification. So verification actually refers to the accuracy of the numerical solution of the governing equation. So that is, if you see, so here the parameters which we giving, that is in the mathematical model, that is mesh, then numerical methods, schemes, all those will dictate the accuracy of the numerical solution. And then the validation is whether the simulation is an accurate representation of the real world that is being modeled. So if you see here, I hope everyone can see my cursor. So this is the actual experiment or the actual reality fluid problem. So that is the actual one. And we, with certain modeling assumptions, we are taking the simulation model. And with certain assumptions, we are actually putting the fluid properties and other inputs. And there are certain approximations and error in the numerical solution, because we are actually approximating it as a algebraic equation. There may be some round off errors and truncation errors, etc. And finally, we are obtaining a simulation results. And this is from reality. If you do some experiments, we get an experimental data. It also got some experimental errors. And if we compare the results of simulation and the experimental, then we get some error margin that is called E. So that margin should be within the acceptable limits. So sometimes if you compare the simulation and the experimental results, you may get 80% close to the experimental results, or sometimes 85% close, or 95% close, or 98%. So you need to always have to quantify what is the error margin you are having with the actual results, so that you will have always that confidence. Okay, I am predicting, okay, with 5% error or 10% error. So that will give you a confidence, and you can actually confident in the process you are using. Otherwise, you will be always in a dilemma. Okay, I have got some colorful results. I don't know how far it is true. So that confusions can be avoided. So these two are the important aspects of any CFD simulation. Okay. So that is all about getting a CFD simulation and how we are making sure it is accurate and the real problems are being captured to the maximum possible extent. We will touch upon an introduction to the turbulence models, because whenever one goes start solving an industrial fluid flow problems, the fluid flow will always be turbulent, and turbulence modeling is altogether a vast topic, and it itself is a big topic, and it is taught as a one full paper in the course curriculum during MTech and all. But with this short time, we will see how far at least the practical side of what turbulence models need to be used at what situations. So those things we will see. So the turbulence is an unsteady phenomenon where the flow is highly irregular. It will be fluctuating both in space and time. It is highly rotational, and there are large and small scale fluctuating eddies as shown here. So you can see, say this is a flat plate. If incoming flow is coming with a free stream velocity of u infinity, and at the starting you can see the flow is laminar, and as and when it encounters friction and flow rate increases, it start transitions to turbulent, and in the fully turbulent region you can see the turbulent eddies, which is of rotating nature, and there are small scale eddies and large scale eddies. So capturing these small scale and large scale eddies, that is the actual challenge of turbulent flow. So then we have a turbulent boundary layer profile. All of you might have studied that in your BTech and MTech courses. So basically there is a region very near to the near wall region, which is called viscous sublayer, and above that there is a layer called buffer layer, and top of that there is a region called log low region. So you can see here at the wall, as you all know, the fluid velocity will be 0, and there is a region where the velocity of the flow is linear to the distance from the wall, and the dominant stresses in this particular region is due to wall shear or due to viscosity. So that is called viscous sublayer. And the buffer layer, the stresses are dominant due to turbulence. Those are turbulence stresses. And in the log low region, the flow is fully turbulent. And so when solving for turbulence, our challenge is to what extent one need to capture. So based on the problem, one has to take a call. Okay, do I need to exactly capture till log low region, or full physics, all the boundary layer regions of turbulent model? So that is what it is being addressed using turbulence modeling. Okay, so the turbulence modeling, usually the commercial softwares available in the market, be it Fluent or Star CCM or whatever. So all those are RANS models. So RANS is nothing but Reynolds averaged Navier-Stokes equations, which are used to compute the flow field. So we have discussed Navier-Stokes equation, and we can, from Navier-Stokes equation, we can arrive Reynolds average Navier-Stokes equation by using, there is a methodology called velocity decomposition, where the velocity is decomposed into a transient and an average component, and that, so the mathematical derivations are long. So, but the crux is like the UVW velocities are decomposed into a fluctuating component and averaging component, and that will be plugged into the Navier-Stokes equation, which results into an additional term called Reynolds stresses. And to model that Reynolds stresses, there are certain approaches had come, and those are called turbulence models. So for modeling the turbulence and for with this additional equation of Reynolds stresses, these turbulence models have come. So there are different turbulence models like K epsilon, K omega, etc., etc. But the whole objective is the whole objective of all these exercises how to capture these turbulent boundary layer regions. And this is near wall phenomenon. And in near wall phenomenon, the gradients, velocity or shear stress, all these will be, there will be higher gradients. So that is the objective of this turbulence modeling. And okay, and RANS is one of the best approach for in many industrial applications because of its computational efficiency. Why? Because if you see here, the viscous layer and buffer layer are small regions near the wall, which cannot, most of the cases, which is not resolved using a computational mesh. So these two regions are resolved using a wall function approach. So wall function is nothing but an empirical approach wherein it obeys the physics near the wall, so that we can calculate the flow parameters over that region, and we just need computational mesh only to capture the log low region. So that is the whole objective of the RANS approach. Now we will come individually to each and every turbulence models and applications of that. Then we will see some more other aspects of turbulence modeling like Y plus and all. So the most famous and commonly used turbulence model in any industrial application is K epsilon model. So the K stands for turbulent kinetic energy, and epsilon stands for the rate of dissipation of turbulent kinetic energy. And when we, so what this model does is, so this model will not simulate the flow in the buffer layer and viscous sublayer. So it just captures the flow in the log flow region. And to capture the physics in the buffer layer and viscous layer, we use the wall functions. Okay. And for this model, the Y plus values are between 30 and 300. I will come to Y plus once I explain all the turbulence model. For time being, let us keep, okay, our Y plus we require between 30 and 300. Let us keep it like that. Okay. And this model is best suited for external flow applications around complex geometry. So when I say external flow applications, basically it is well suited for bluff bodies. That is bluff body, when I say like flow past a cylinder, flow past a sphere, or flow around a car, or flow around a truck. For those kind of applications, K epsilon model is one of the best model. And it is not suitable for flows encounter adverse pressure gradients and strong curvature in the flow. Like these models are not suitable for where there is an adverse pressure gradient, or if there is a pipe with a lot of bends, then it's an example. So where these models, K epsilon model will not be a good choice for modeling those kind of things, those kind of flow applications. Okay. And this is another famous model, K omega model. So where K is the turbulent kinetic energy and omega is the specific rate of dissipation of turbulent kinetic energy. And it is otherwise called a low Reynolds number model. And here we try to capture the viscous layer and buffer layer.